A use case on Agriculture 4.0. Actually, we are going beyond the simple machinery. We integrate sensors in there, and then we integrate all the data into a holistic, complete ecosystems. And we'll walk through about that in the next slide. So we'll see the use case in the domain, in the Agriculture 4.0. We'll see further development, and then the IPR associated to that. So actually, we studied a patent from Claas, a famous harvesting machine on agriculture machine manufacturer. And to really simplify it, let's take a field, different fields like this, and with 3 harvesting machines that are harvesting different crops and different crop yields and so on. Different machines also, it could be different brands, and there are several trailers traveling from one harvester machine to the silo to get the crop. And the problem is actually that we don't know, in the usual case like this one, we don't know when to meet in the field. So maybe the trailer will wait quite long because the black machine is not ready yet to offload. Maybe the other harvester will wait because there is no trailer at the good time and good points in the good location on the field. So the next step is integrating in the next slide is integrating sensors in the machines on the harvesters. Next slide, please. Yes. Integrating sensors into the harvesters and also into the trailers, so that we can monitor the level of charges not before. The level of charges into the tanks, and so we can have, using database, including all the speeds of the machine, the capacity of the machine, different maps. We have geodata related to the environment. We know the crop yields, or we measure the crop yields. We know the machine, the type of machine, so we know the performances. So we can simulate at very often, high rhythm, the rendezvous time on location that is optimal to optimize the use of the resources, which are the trailers in this example. So for example, if the harvesting machine, the yellow one, is loading, is about to need offloading very soon because the crop yield is important, the performance of the machine is important, then the system will allocate the orange trailer to the yellow harvester. And if there is something bad going on for the first harvesting machine, maybe the system will redirect the orange trailer to another one. Okay, it does that on a day, minute to minute. In the next slide, we'll see that there is another trailer going to the black harvester, and everything is dynamic and everything is resimulated every time. So that's the theoretical, let's say, use case that is using Claas in his patent. Is describing Claas in his patent. The benefits of that is that it's really an optimization of resources, meaning that in the classical use case, there would be maybe 7 or 8 trailers to offload all the machines at the same time. But using this system, maybe you just need 4 trailers to do the job. So it's really optimizing the resources of the machines, and also less cost, because less machine, less people, and less gas cost. It's also decreasing a lot the soil damages, because actually when there are so many heavy machineries on soil, the soil gets compacted, and then the yield next year will be lower because of the compaction of the soil. So having the machine really meet at the good time and good position in the field really helps decreasing the soil damages. So that's the theoretical view of that. Now on the next slide, we'll see how Claas implemented that. So actually, what they do is that they created a platform where everybody is joining in there to share the different data. So Class had an application on the platform, which is the telematics, where it collects every data from all the machinery on the field. And together on this platform, there is also a route planning and route optimization application that is actually coupled with the Class telematics, so that we can on Lycos, yeah. So it's another partner that is joining into the ecosystem, and together they are implementing this use case. But also in the ecosystem, we can see there is Michelin application where actually they use data from the ecosystem to suggest a pressure of the tires or the machinery that is going on the soil, depending on the type of the soil, depending on weather. And so when you need weather, you need an application for weather. So you have another partner, which is Meteo Blue, which is providing weather information to the rest of the community on the ecosystem. And likewise, you can have many other applications. One is about crop and seed planning. Another one is on farmer planning. Another one is on all the chemicals. You can use the phytosanitary chemicals from BASF. Actually, they imported all the catalog in there so that the people can choose directly, or it can be automated selection according to yields, according to the type of crops, the weather, and so on. And there is even one for fertilizer planning, for example. And everything is inside an ecosystem which is called 365farmnet.com. And it's actually a real thing. You can download an application on your Android or iPhone without problem. And it's gathering all the access to that. And how they appropriate the value during this is actually by on the next slide. It's some kind of a freemium approach where there is basic function on components on apps that are free. And you get, for example, field mapping services. You get many services like this or apps that are totally free. And then if you want to go further and to go deeper into the use of the data of the ecosystem, then you can buy all the components. It's a fee-based planning, so that actually you can get more services about that, and you really create an ecosystem around that service. So that's the illustration, the real world, how a hub monopoly works, a hub platform works. And I leave the rest to my next colleague to develop further the use case.
Thank you, Nicolas. Now we have to focus on a further use case we will identify and develop. We have identified this intelligent fertilization planning that will try to extend the boundaries of the system and will try to deliver new solutions and provide new and more extensive benefits for customers. And for that, we have to take a whole picture of the whole life cycle of the crop and gather all the information. We can see in terms of the seeds that are going to be used, which type of seeds will be used in the crop, which conditions have all the environment conditions like the weather, the ground, and all that stuff. And all this information is customized somehow, meaning that it's individual and specific information according to specific needs and concerns of customers. Then having a look at the package of practices, we identify all inputs and practices and have a look to the whole timing control in the crop life cycle. Then from the crop care, we see at this point of the crop, we identify if needed, which type of pest is needed and what is the best solution to be applied for the product. And harvest and post-harvest, we see here when is the right time to fertilize, how in which manner is the optimal for ensuring the quality, and also will help in terms of logistics, meaning that we have for optimizing the storage management, for example. And then we come to the end of the life cycle, looking forward and going to the next crop. We will gather all the information, know all the timings and when is the best time for late or early harvest, the conditions that will affect. And at the end, we go from the initial use case that Nico explained before, that was using all the data from the vehicles in order to optimize the routes. And we use that for using vertical networking, meaning that all this information that we have gathered and all the data will be used and communicated through the network and to the community by delivering this service to the customer. And at the end, all these will help for optimizing in terms of improving the product, mitigating risks, or increasing efficiency. Now, Christian, we'll go with the next slide.
Yeah, thank you, Ricardo. So we propose now to visualize the implications of moving from a value-added monopoly IP strategy to a hub monopoly strategy. And to do that, we use the two models, the business model template and the 360 degrees IP strategy template, to highlight some main differences. So here, I would like to highlight the changes in the range of value creation partners first, having farmers and cooperatives on the left side, and expanding this range of actors and partners to the entire actors of the plant life cycle. We also need new competencies to move into the hub monopoly. It's not sufficient anymore to have mechanical and automation and sensors. You need to cover also biology. You need to be more elaborate on big data analytics as well. And then in terms of customer relationships, moving from the left to the right picture, everything gets more virtual and happens mostly on an application, on a platform, which offers also a great flexibility and a huge scaling up potential. If now we move to the IP 360 degrees model, here I would like to highlight the upper left corner first. Moving to the hub monopoly, it means you need to be even more careful about infringing third-party rights because of the vast amount of digital patents. And you certainly also need to consider whether you need to contract licenses to get access to some standards. On the lower left corner of the model, moving again from value added to hub, you need, of course, still to protect key user relevant features, but on top of that, you need to protect the elements of the ecosystem and basically to protect the use cases instead of the features. And finally, on the upper right corner, exploitation and appropriation is achieved by promoting the benefits of joining the ecosystem and earning, basically earning platform usage fees. With that, now I hand over to my two next colleagues.
Okay, so thank you, Christian. Now we have seen a lot about the business model and the 360 degrees IP strategy. We will now look at the use case outline to try to and so we can see that in somehow kind of a process on the left-hand side by what data is available in the cloud, in the class and the FarmNet system. So we have the first box here, which is dedicated to analytics and data that are available from the harvesting and trailer machines that we have seen in the first part of this presentation. And so some example here could be yields or soil data, for example. On the second side, as data have else sitting into the cloud, weather, and so on. So from that, we have a lot of data, and the question and the goal here of this use case is to make something available to provide a service to the farmers. And therefore, the big part of making this use case real is about algorithm development and model to make this available on the net. So we can, from this data, create basically treat this data in order to create a model and simulation for fertilizing processes. And so I was detailing about the data available. We are able to make a model and simulation for fertilizing. From this model and simulation, it's possible to propose a service to the farmer. And this service can be either considered as proactive or reactive. In a proactive manner, we can imagine a kind of a contract between the farmer and the platform. And basically, the farmer just does not take care anymore about the fertilizing, and is designated to put the good fertilizer at the good time at the right place. And so this is maybe more the think also about an alternative, which is the
now we have a good understanding of the fertilization service use case. Let's jump to the IPYs that can be used to protect this service. First of all, we can use patents. We can use digital patents, especially the one to process the exchange between the fertilization service provider, the spreader, and the different actor related to how to best use the fertilization. But we need not to forget about the good old mechanical patent, maybe, for example, patent related to mechanical interface between the fertilizer container on the machines that can be used to do the fertilization. And also at the boundary between digital and mechanical patent, maybe tag can sort of try to protect, we shall try to protect tag on the containers that determine what is within the container, which type of fertilizer we are within this container. Secondly, we can use copyrights to protect, I would say, true aspects. We shall protect the software used to monitor, interpreted the data related to the fertilizer, how to use the fertilizer, which quantity of fertilizer, which type of fertilizer. We shall also use data protection, sui generis data protection for the database that will gather all the information regarding to the fertilizer, how to use this fertilizer, all the one related to the platform. And now Vijay will explain us regarding design IP, trademarks, and trade secrets.
Thanks, Adrian. The next is the design IP. So design IP can be created on the basis of human-machine interface of the apparatus or software dedicated to the configuration of the service offered by the fertilization service provider. So the next is the trade secret. So regarding the trade secret, the combination of the fertilizer can be kept as a secret, where the ratio among the multiple fertilizer based on their different needs of the soils and crops, that can be thought through, and it can be kept as a trade secret. So the next is the trademark. So trademarks related to the devices such as container of fertilizer or machines working together with the fertilizer service provider. So those kind of combination of the trademarks can be created. So these are the IP rights which can be further extend the service use case. Thank you very much.